Okay. Hello, everyone. Let's begin. Please, I sent data to some Google Drive. I don't know if, I hope you've all downloaded it. Some landslides imagery and district shapefile. I uploaded this data, so kindly download it. That's the name, Landsat 9, from the Google link that was shared. We are downloaded. Everyone has downloaded. It has been downloaded. Okay, so once we download today's data, let's finish one last analysis we're supposed to finish yesterday. Yeah, so we are going to finish yesterday's temperature analysis. There's one last calculation that we will learn about, then we'll continue to today's lesson. So please kindly pay attention whilst you download today's files. So we are going to start by loading our temperature data set from yesterday. So we are using this data. Sorry. So we are doing this one last calculation, then we move on to today. So kindly input this raster data set from the temperature folder that I sent yesterday. Then you add to your layer. So yesterday we calculated sum and average for rainfall. You can use the same process for temperature data. Today we are coming to also calculate some thresholds in temperature. You can also use the same formula for rainfall. So first, we are going to export this to GeoTIFF file. By now, we are all familiar with it, so we can easily do that. And we'll name it temperature. It's a temperature data from 2011 to 2020. You can give it this name. And then you can go ahead and specify your coordinate reference system. When you're done, then click on OK. So you can deactivate this one and minimize. So we want to find, what we are going to do right now is we want to find areas that are exceeding below a certain value. For instance, we want to find areas that are maybe above 20 degrees for a certain time period, or probably below 5 degrees. So from here, we are going to open our raster calculator. Majority of the raster analysis, if you have any calculation to do, this is the tool that we use for. Now in the raster band, you realize that you have at 1 to, if you scroll down, at 120. Now this data is a monthly data set from 2011 to 2020. So between those time periods is 120 months. As I said yesterday, if it's a monthly data and it starts with 1, it shows month 1, month 2. If it's a daily data and you see maybe month 1, it shows day 1, day 2, up to that number. So let's say in 2011, the first month, we want to calculate how many regions or locations that were probably below 5 degrees, or let's use the example. Or how many locations that was greater than 5 degrees, any of them. So what we are going to do is we just double click. We are using the first month. And then let's use maybe greater than, an example, 20 degrees. Let me zoom in. This is the expression we are using. We want to know the locations for the first month of this time period that was greater than 20 degrees. So from here, you have to specify where you want to input your output layer. So we can name it maybe temperature underscore, then the sign greater than 20. This is the name I have given to my output layer file. When you're done, you click on save. Oh, sorry. Omit the, When you're done, you click on the save. Make sure your output format is a GeoTIFF format. Then you can go ahead with OK. So areas that you see that are dark are areas that are greater than the 20 degrees. That's the first month for 2011. And the first month is definitely January. So you can go to properties, change this to the pseudo color, then discrete, move to our equal interval. Then we apply. I want to choose a different color band. Yeah. Yes, I was saying that because most have not downloaded today's zone, we'll continue with what we did yesterday. So we are using the temperature data from yesterday. So if you want to change the position of your colors, you can use the invert color ramp. I want the areas that are greater than the 20 to show the darker red. So, why is it? I made a mistake somewhere here. Yes, so we have something like this. Likewise, we can do another one where we look for cold regions. I guess so. Is everything okay? Okay, so let's do another example. We want areas in the second month that was, let's say, less than maybe -2 degrees. So we specify where we want to save that. Temperature. Then we name it. The output CRS is already there. You make sure this is GeoTIFF. Then we move on to OK. After that, you can style your layer. So depending on what you are working on, if you want to see areas above or below a certain threshold, you can use the raster calculator for these kind of analysis. So that was just the last bit of it for yesterday. Please, I believe by now we all have the Landsat imagery on our laptops. They are still downloading. Please, I'm giving 5 more minutes for the download so that we move on. Yes, it's still downloading. Sorry? Yeah. Is I also still downloading? Oh, yeah, done downloading the data. No, for today, the Landsat image. Yeah. Oh, okay. It's not easy. Have you downloaded today's data? Okay.
Is it day 3?
It's day 3.
Which folder?
Hmm?
Which folder?
Downloaded today's data. Okay. That's it, today. Yes, I'm giving you time for that. Continue. Please, if you are done downloading, kindly extract the files to your folders. Okay, so for today, we are going to calculate some of the indices that we use for our daily works. That's NDVI, Normalized Difference Vegetation Index, Normalized Difference Water Index, and the Normalized Difference Built-Up Index. Later, we can also look at calculating land surface temperature. So for this, we are going to use the Landsat 8.9/9 imagery. For that, you don't really need to do much pre-processing. So it's a ready-to-use kind of imagery. That's why we are using that for today. If you are using anything below that Landsat imagery, that's the 4.5, you would have done some bit of processing. And I think you've done that in the NV class, right? Yeah, the NV class. But today we'll just use the Landsat 8 imagery. So so first we'll start with the normalized difference vegetation index. So for that, kindly let's navigate to our downloaded Landsat imagery. Please make sure that you have these important files. That's the MTL, the band 3, band 4, band 5, band 6. You see B6, B2, B3, B4. It's called band. And then the band 10. We'll be using band 3, 4, 5, 6, and band 10 for today's class, as well as this file. You see a text document with the last initials MTL file. We are also going to make good use of that. So first we'll start with NDVI. For that, we use it to calculate the amount of vegetation, usually used for vegetation analysis. Check the dense vegetation in an area or healthy vegetation in an area. So to start the same process, go to Data Source Manager, Raster, locate your Landsat file. So please, we are going to input the file that you see TIFF at the description. The item type, TIFF file, that is what we are going to use, not the ones that end with the AUX. We are going to use the TIFF, GeoTIFF files for this process. So the ones that end with the RB3, RB4, RB5, RB6, that is what we'll be using. So you can select those 4 images. We are loading in the band 3, band 4, band 5, and band 6. So you select those images, you open, and then you add it. Yes, 3, 4, 5, 6. You should see 3, 4, 5, 6. These ones. Please, I hope we are finding the 3, 4, 5, 6. Are you okay? Yeah. So before you see it, kindly extract the folders. So for the NDVI, we are going to use the red band and the near infrared band. The red band for Landsat 9 is band 4, then the near infrared band for the Landsat 9 is band 5. So we are using these two bands because it measures the light that is usually reflected by vegetation. That's why we are using those bands for the NDVI. Please, are we ready or we still can't find it? I know you are ready. Please, we are starting. So to make it easier for us, we can rename the bands. If you double click on, let's start with the band 6. If you double click on it, you go to source, you see this long layer name. You can change it to band 6 so that you don't get confused during the calculation. So we are changing the layer names for the bands that we've loaded. You double click, you go to source. Then under the layer name, please make sure that you are giving the correct layer name to it. Please rename your layers to make it easier for you during the calculation. You just double click and go to source, you see layer name. You change it to the band name. Please make sure that you are renaming the correct band. So kindly rename it this way and let's move on. I'm giving some few seconds to allow you to finish renaming. Okay, so let's move on to detecting our vegetation. For NDVI, we are going to subtract the red from the near infrared, divide it, and then add the near infrared plus the red band. There's another file in the Google Drive. So this is what we are doing right now. This calculation. We are calculating for NDVI. We want to detect areas with dense vegetation or areas that has low vegetation. So if you can find this file, you can open it so that it guides you. Okay, so the next step, we are going to our raster calculator. Make this a little smaller. So this is our calculation for NDVI. Near infrared minus red divided by near infrared plus red. Near infrared is band 5 and red is band 4. So we are going to just do this. First bring your brackets and then our near infrared band 5 minus our red band, that is band 4. You then close the brackets, bring the division sign, another open bracket, then our band 5 plus our band 4. Then you can close the brackets. We are using this equation to detect our dense vegetation, areas with dense vegetation, and areas with low vegetation. This is the equation. If you are adding the image to the expression box, you can just double click, then use any of the operator signs, and you continue. Okay, as usual, when you are done, you are going to give your output layer a name. And we are going to name it NDVI. Always make sure it's in your GeoTIFF format. If you are done with the equation and you are done naming the file as the output layer, you can go ahead with your OK. This is the formula again. So band 5 minus band 4 divided by band 5 plus band 4. So there's an example. Are we okay? Okay. So we have our NDVI here. We can change the colors so that we see clearly the areas with the dense vegetation or areas with the low vegetation. You can see more color ramps if you place your cursor to the all color ramps. Then as usual, our equal interval. Then apply. Use the greens. Bring it to the top. When you are done with your analysis, kindly move your band to the, below your analysis. The difference is not too clear, so I'll change my color ramp. Manage it like that. Okay, so the values you see here, if you have -1 to, let's say, 0.2, they usually indicate areas with bare soil or water. Between the 0.2 to 0.5, we say that there are areas that are maybe grasslands. If you have values above 0.4, maybe to 1, then we can say that area is characterized by dense vegetation. If you want to know a particular part, you can just use your identify to check the values for a particular location. When you are doing your projects and your works and you have your boundary shapefile, you can use the process of the clip by max layer to extract the NDVI for your region of interest. Okay, now we are going to move to NDWI, which is also a similar process, but that is used to detect moisture content in vegetation or soil or water bodies. Are we okay? Thank you. So we are going to calculate for NDWI, that's normalized difference water index. This is for vegetation. Now we are doing for detecting water content in vegetation, soil, and also water bodies. So the same process, raster calculator. For NDWI, this is the equation. We have our green band. We are multiplying the near infrared band from it, then divide and add the green and the near infrared. So we are going to do this same process. So for this, it will be band 3 minus band 5, then band 3 plus band 5. Any band we use for a particular process, it just shows that that particular band reflects more of that feature on the Earth's surface. So similarly, like the NDVI, we open our brackets. So green minus NIR, that's band 3, minus the band 5. We close that bracket. We divide. Then we add our band 3 to our band 5. This is the equation for detecting water. So this can usually be applied to detecting vegetation stress or irrigation needs, anything that concerns water analysis, and also detecting wetlands. We can use this for that. So when you're done with your equation, you select where you want to save it. This will be our NDWI. Then we click on save. We specify our reference, coordinates reference. When you are done, you always make sure your expression is valid, and then you can go on with OK. So you can see the values here, greater than this, showing that areas have a lot of water. Below -1 or 2 -1, you get areas with little or less water. Usually, if you are studying some drought analysis, you can also use this for that. The same way, we are going to change the colors. Since we are detecting water, let's make it blue. We want the areas with the high values to have the deep color. So we do this, apply, and OK. Oh, let's change it, sorry. Yeah. Okay, we are good to go. This Landsat is from Taiwan. It's a little island, so it's mostly surrounded by water. So that is it for detecting water content. Please, your assignment will be to clip to your study area and create maps for these indices. Okay, so last, let's move to NDBI, that's normalized difference built up index. The index, or let's say the indices are so many. So depending on what you are working on, you'd have to learn the one that is right for you. But today we are focusing on these major 3 ones, the vegetation, water, and the built up index. So for the built-up index, is as the same way to detect areas with built-up construction, anything that is man-made. You can use that for any form of urban analysis. So for built up, our equation is the short wave infrared minus the near infrared divided by short wave infrared plus our near infrared. So our short wave infrared is band 6, and as usual, our near infrared is the band 5. Okay, so the same way, same calculation. Let me uncheck these ones. Same raster calculator. We open our brackets. We are doing band 6 minus band 5. So our band 6 here, you double click, subtract. Band 5, you close the brackets. You bring your division sign. Open another bracket, then our band 6 plus our band 5. Then we close it. This is the equation for detecting built up areas. When you are done with this process, again, specify where you want it to be saved. We will name it NDBI. When you are done, you can click on OK. So all these indices, usually the values range between -1 to +1, where 1 shows that if it's vegetation, that means high vegetation. If it was water you were working on, means areas with more water content. If it's a built-up index, it means areas with high built-ups. So again, we can change these colors. We symbolize our layer. Let me search for another color. You can always use the identify tool to search for your area. Okay, so if you go to your browser, kindly locate your OpenStreetMap. This one right here under this browser. We want to activate one of the base maps to clearly see where these vegetation or let's say water or built-ups are really high. When you go to properties, another thing you can do on your raster layer or any type of layer is to reduce the transparency. So I'm doing this just to see the areas with the high build-ups and areas with the low build-ups. This is in Chinese, so sorry. My laptop is in Chinese. But yeah, anytime you want to see an area that is below some analysis that you've done, you can activate the base map, reduce the transparency of the layer so that you can see where it is falling on. Let's take some few minutes break so that I can finish your calculations, and then we'll move on to the next. Yeah, under here. Come empty-handed. Where's your laptop? You want to change the color? Oh, right click on the layer. No. The layers, yes. Right click. You can double click or right click any of them, yeah. Then symbology. From here, you are okay with it, right? No, pseudo band, yeah, that one, pseudo color. Then you can change the color from the drop down. No, you see, yes, yeah. Yes. Something that you can clearly see between the values. You can choose that. Then please change the linear to discrete. The linear is on top of the colors, just above the color. No, you see there's inter. Here, this linear, yes. We are changing to discrete, here. And then you scroll down, not this one, use this bar here to change the continuous to equal interval. Yeah, when equal interval, that one allows you to change the classes. Yeah. So 5 is okay, then you can apply an okay. Apply an okay. Yes. So if you have any shape for, you can clip to your steady area. The best. Are you okay? Do you understand? Ah, okay. Miss Aida, or you're still on it? Okay, I'm moving to the next. Oh, we are even done with the. Oh, okay. Please, if you are done with all the indices, go ahead and load in the band 10 from the folder that we sent. Add the band 10 to your layers. Please, when you load your band 10, kindly rename it. Please add your band 10 to the layers. When you add the band 10, kindly rename the band. So our next part is to do land surface temperature. And for that, we use the thermal infrared band, that is the band 10. For this, the calculation is a bit complex. It's a really long list. Let me send this file to the WeChat. It's a good. I've sent the calculation of the land surface temperature to the group. So for this calculation, this long calculation, we simply want to know how hot the ground is or how hot the surface is. So for that, we are first going to calculate top of the atmospheric spectral radiance. Then we convert that to brightness temperature. And then we include our NDVI. proportion of vegetation and calculate the emissivity. When I'm sending the step-by-step guide, I'll include the in-depth explanation of these plenty figures. So first, we have to start with the calculation of our TOA. There's an MTL file located in the Landsats folder I sent to you. Please, this one, this file. We need some information from in there to enable us calculate the land surface temperature. So please, we are going to open this file. Please, this one. Where is it? Please kindly locate this file in the folder, that's the Landsat imagery folder. It should be the third one, ends with MTL. Okay, so our first equation is to calculate the top of atmospheric spectral radiance. For that, this is the equation. ML represents the multiband 10, which you will find in the MTL file of the Landsat image. Simply, the MTL file is the description of everything concerning the images you have. So where when it was launched, the characteristics of the bands, you can find everything in this MTL file. Please make sure you don't edit it by mistake. It's very important. Okay, so we are starting with our first equation. We have to multiply the radiance multiband 10 by the band 10 that we added to our layers. And there's also a radiance add band 10. So we have to first find our radiance multiband 10. You can use the Control F, then you type radiance. Please, we are searching for our radiance multiband 10. For land surface temperature, we work with all the values concerning the band 10. So we are looking out for this. This value that we see here. In the text document I sent, I've already done the conversion. You can see it here, the ML, etc., etc. Yeah, so the same way, we use our dear Raster calculator. Go to Raster calculator. We are calculating for this one first. So our first equation will be the radiance multiband 10. That's the 0.0003. You can simply copy that. But if you are doing your own work with your own imagery, please be sure to check what kind of values your imagery has from its MTL file. Next, we have to multiply it by our band 10, and then we add 0.1. So you use the sign and then you multiply it by the band 10. Lastly, we are going to add our AL here, which represents the radians at band 10. You can also find that in the MTL file. If you scroll down a bit, you see the radians band 10 here. We need this value to assist us for the calculation. So you can copy the 0.1. Make sure you are copying it from band 10. There are so many bands here, so from band 10. And then we add it to our equation. So this is the first step and the first calculation for the land surface temperature. We call it the top of the atmospheric reflectance. This is the equation, 0.000380 times band 10 plus 0.1. When you are done, same process, we specify where we are saving it. You can name it TOA instead of typing the whole name. Then we save. When you are done, you click on OK. No need to change the colors for this one because that's not the final results. So our next equation for detecting land surface temperature is the brightness temperature. Let me give you some few minutes to finish the first one. So we are moving on to 2, where we convert our TOA to brightness temperature. So brightness temperature is more of what the satellite sees or assumes how hot the Earth's surface is. For example, like guessing how warm or hot someone is by simply like touching their clothes. That's how the brightness temperature works. It's like the satellite guessing how hot the surface of the Earth is. So we have to also calculate for that one to add to our equation. So for brightness temperature, we have the BT, open bracket K2/N, another bracket K1 slash the L plus 1. Then we subtract it from 273.15. Okay, let's move on. So once again, we have to find our K1 constant band 10 from our MTL file. You hold the Control and F, then type the constant. We are looking for this too, the K1 constant band 10, then K2 constant band 10. Once again, please make sure you don't edit this MTL file by mistake. So we are looking for these two for our next equation. So let's move on to QGIS to calculate our brightness temperature. Go to Raster calculator. Let's check it again. Our K2, according to our MTL file, is this figure. This figure here. You can copy and paste because I already did that. So hold on. The summary validate open bracket. Bracket open in that. Hold on. K slash N K slash. In 7990284. Okay, 0284. Please make sure you are inputting the right equation. Okay, 1 plus 1. Two 273.15. So I'm done with adding my equation. You find the values in the MTL file. So it's 1329.2405. That is the K2 from our MTL file slash the IN. Please don't type the IN on your own. There's IN here. Then our 799.0284, that's our K1 from our MTL file. Then we divide it by our TOA, the one that we ran few minutes ago. Then we close the bracket, you add +1, you close the entire equation for the first one, and you subtract from the 273.15. Make sure your expression is valid. When you are done, you go and save it. So this is our brightness temperature. So let's just name it BT. And our project CRS, and we click on OK. The next step is to calculate NDVI, but we already have NDVI. So skip that one and go to the next. Kindly change your NDVI back to the single band gray. Change the NDVI to single band gray. To avoid confusion, you can delete the other ones, that's the NDVI and NDWI, and leave only the NDVI. To avoid confusion, yes, you can delete these two and leave just the NDVI. So maybe we don't need this again. So you can delete them and just leave the NDVI. And I said once again that you should change it back to the single band gray. The next step for the land surface temperature is the NDVI, but because you already have it, we'll move on to the next one. That is the proportion of vegetation. And for that, we need the NDVI to calculate it. Okay, so again, to raster calculator. For our proportion of vegetation, this is our equation. The NDVI, then you subtract the minimum value of the NDVI from it. Then you divide by the NDVI maximum value, and you subtract the minimum value from it. In all, you put them in brackets, then you square the equation. So we open our equation, NDVI minus the minimum value. Our minimum value is here, right here. I made you change it to the pseudo band gray so that I can see the minimum and the maximum clearly. So we are just going to input our 0.127756. Then you can close that. We divide by, you open another bracket, our maximum value minus the minimum value. So 0.628908. Then we subtract the minimum value from that. 1, 2, 5, 6. Close our brackets. And then you can see a sign, little sign here. That's what we use for the square, the one under the ABS. We square it and by 2. So this is our equation for the proportion of vegetation. Let me zoom in. I'm waiting for you. Please, after the 2 is just a cursor, so it's not a number. Let me even take it off. Yeah. So this is our equation for proportion of vegetation. These values you see there are the minimum and maximum value of our NDVI. Okay, if you are done, you specify where you want to save it. This is a proportion of vegetation, so let's make it a PV. Now we have our PV. The next part is to calculate for this E in the land surface temperature equation. And this is our E. That's 0.004 multiplied by the PV that we just did plus our 0.986. So again, raster calculator. You can check the equation in the file I sent to the group. Then we multiply by our PV. And the next is to add up to our 0.986. The same way we specify our output layer, we name it E. Let me zoom in so that you see the equation. Okay. I'm moving on. Name it. Then we go on with, okay. Are we good to go? Are you confused? Are you okay? Please try and input it manually. Sometimes if you copy and paste, you get invalid. You are not okay? You are lost. Okay. How far? What's the time? Okay, now to our final step. Please, in this equation here, this is IN. There's a little typo here. Kindly change it to IN. So our final step is to finally calculate our land surface temperature. And we are going to use everything we've done for the past 20 minutes or so. Our final step is our land surface temperature calculation. And this is our equation. Which theory? I'm confused. Yeah, we use the values from the MTL file. This one. This one. The no. It's the NDVI minimum and maximum values, not the theory. These ones. Do you understand? The minimum value for the NDVI, not the theory. That's if you are calculating for the PV, right? Yes. Shall I continue now? Okay, so lastly, our land surface temperature calculation. So we go to our raster calculator, open our brackets, and we are using our BT. BT/1 divided by 1. Then you close this bracket. Oh, is everything okay? Please, I'm waiting for you. Okay. The BT divided by 1 plus our W, our value for that is 10.8. Then next is our BT, that's the BT that we did here. Divided by this figure. Then we close our brackets. We multiply by, we use this operator here. Then we we bring in our E. Open, close, plus W. This is our final equation for the land surface temperature. Our brightness temperature divided by 1, then a W figure, a W number that's 10.8, then our brightness temperature, so on. See the tiny, I don't think you see is multiplication. Are we done inputting our values? Okay, so if we are done, we can name our final layer as LST, that's land surface temperature. We save, specify our CRS, and then we click on OK. So when you are done, as usual, you add your, let me change this. Move a little clouds in there. You can do, I think in the beginning, you were taught how to use the NV for processing. You can also use QGIS for processing, but unfortunately, we will not be able to get to that point. So now you can see, you can change the colors so that you see the areas that are emitting an amount of heat more than other areas. Okay, so you can clip this to any district of your choice. I sent a district shapefile and then create some maps. Yesterday we created a map. I'm here to see your inputs. The certificate will give them tax. I'm asking. That's all we'll do. Ah, okay, then that's. So please, any questions? Expression. Ah, you want the equation? This one? Or you want the actual values? There's the equation. Hmm? 10.8. Some of the numbers are constant. Yes. So if you have an image like this, you make sure you process it. Maybe it's better to process in NV before you so that I don't get these things. I can't see the sound to see the values. Yeah. The W, some values are constant, like these numbers.
They're constant.
Yes.
This one.
Yes.
And applies to.
Yes.
How? Where can you get them?
Sometimes it's those who do the soft. No, we don't cook them.
They are where?
Yeah. So I'll give the explanation in the step-by-step guide.
Because they just copy and give chicken.
I did not cook it. Come. I finished. So we should finish in 3 days. Yeah. You come with the laptop. Hey, without the laptop. And you'll be asking questions the most. Are you okay? Yeah. So I'll send a file so that you can hear. Awesome. Hmm? Yeah, so please, for those who got stuck somewhere, as usual, I'll send the step-by-step process so that I can follow that one. Yeah, so we are done for this QGIS software. Next week, another person will take over with ArcGIS. Thank you too.